All right. Okay. So we're going to pick up talking about graphs today, right where we left off last time. So just as there's many different tree traversals we saw last time, pre-order, in order, post-order, level order, we also saw that there's many different graph traversals. Okay. So this right here, we talked about the DFS pre-order, which is the order in which we call DFS recursively from previous lecture. Then we have the idea of the post-order. It's the order in which DFS returned. And at the end of lecture, I posed a challenge, which maybe some small number of you attempted, which was to attempt to come up with a way to do what I call a breadth-first search, which is the equivalent of level order in a tree. So you start at 0, then you visit all the vertices that are 1 away, then you visit all the vertices that are 2 away from the source, and so forth. So what are the vertices that are 2 away from the source in this graph? 2 and 4, I heard. Yeah, these are the ones that are 2 away. What are 3 away from the source? 3 and 5, right? And then 6 and 8, and then 7. Okay, so that would be an example of a breadth first order. We're going outwards from the source. Okay. So the question again I challenged you to attempt was try and do this. I guess if you're watching the webcast, which I'm recording today, hello, then go for it. But I'm just going to spoil it for you. Okay. So this is the traditional solution, which is that we're going to start by creating a queue, and I'll tell you what a queue is in a moment, that's going to contain the starting vertex S and then mark that vertex. And I'm going to do a demo of this. So what is a queue? A queue is basically like a deck, except you get in the line at the back and you exit the line at the front. It is a normal line, like you're waiting in the line at the grocery store, or if you're a British English person, it is a queue. And so we'll call this queue our fringe. And the reason it's called the fringe is it's the extent of the things we're currently exploring on the graph. It's what's next, right? It's on the fringe. And then what we're going to do is we're going to repeat until this queue is empty, the following. We're going to take the vertex that's on the front of the queue, whoever's at the front. And then for every unmarked neighbor, we're going to mark it, set the edge to, and then add it to the end of the queue. Very similar to DFS. Okay. So let me give you a little demo here. So this actually makes sense and isn't just sort of like, okay, that kind of makes sense. We're going to make it not just kind of make sense, but really make sense. So what I'm going to do here is, again, I'm going to initialize the fringe with the starting vertex. And let's say the starting vertex is 0. So down here, I'm going to have the queue represented. And so initially, the queue has 0 in it. And we mark that vertex as true. Okay. Now we'll do this repeat until the fringe is empty process. Okay, so we take 0 out of the fringe. And then what we're going to do is consider all of 0's neighbors, which are 1. And then we're going to stick them in the queue in no particular order. And we'll also set the edge to and distance to as before. So the distance to 1 is 1. And the edge to get to 1 is 0. This says where you came from. Okay. Next, we take 1 off the queue. And then we're going to take both of its neighbors, 2 and 4, and put them in the queue. Okay. And I'm also going to mark them both, set their edge to 1, and their distance to 2. Okay. Now, this queue, because this is the next elements that are going to get visited, this guarantees that 2 and 4 are the next vertices that will get visited next. That's different than depth first search, where you're going, imagine that XKCD date, where you're thinking about dangers, then snakes, then antivenoms, and so forth. Here, we're forcing ourselves to consider things in the distance of the source by enqueuing all the vertices that are next. Okay, so what are we going to do next? So we have 2 and 4 in the queue. So who comes off? I didn't really make it clear, but 2. Let's say 2 is the front of the line. And so once 2 becomes the active vertex, now we're going to take all of 2's neighbors. And how many neighbors does it have that are unmarked? 1. And that vertex is 5. So we're going to put 5 at the end. And we're going to give it an edge to value of 2 and a distance to of 3. Okay, so I've been saying these distance to and edge to values, and you might not have fully digested what they are. So first one I'll talk about that's maybe slightly easier. Why is this 3? What does this mean that it's 3? Yeah. It's the distance from the source. It's how many hops I've made. Okay, so it's whichever distance, like however far it is to 2, how far is it to get to 2? Well, it's 2 coincidentally. So 5 is going to be 1 more than that. Okay. If we had some notion of edge weight, like maybe this weight of this edge is like, I don't know, 6 or something, then maybe that's 6. But here we're assuming all of our edges are equally costly to cross. We just care about the minimum number of edges. So I'm just going to add 1, hard-coded 1. How about this 2? What does that mean? Someone else. Yeah. Right. So we could have gone 0, 1, 4, 5. But that's not the path we took. We came from 2. This is the previous node in the path towards this vertex. Okay. So we have 4 and 5 next. Now, really important point. What we'll notice is that 4 and 5 are nodes that are close to 0. They're not as far away as 7 or 8 or 6 or 3. Which one is closer to the source between these two? 4, right? It's only a distance of 2. Which one's at the front of the queue? 4. So the queue is ensuring that the closest thing's always at the front. That's really important. And because the closest thing's always at the front, we're always going to explore the nearer vertices as soon as possible. So 4 comes off, and it has one unmarked vertex, which is 3. It goes here. It has a distance of 3. Okay. What's going to be the active vertex next? Where's this V going to go? 5, right? So it hops down there. We had 6 and 8. And so again, I want to note this really important point. There were always visiting vertices in the order from the source. And there's another slightly more complicated invariant, is that at any given time, all the items in the queue have distance either k or k plus 1. So at this point, k equals 3. That's the distance to 5. You'll notice that all the vertices on here, they have distance either k. So vertex 3 has distance 3, and 6 and 8 have distance 4. And not only that, the vertices that have distance k will always be ahead of the k plus 1 vertices. This is what makes this algorithm work. Any questions about this? So basically, the queue is forcing us to visit vertices in increasing order of distance from the source. By contrast, depth first search just dove straight in, and it went as deep as possible. Here, we're forcing that breadth with a queue, with a data structure, hence the class. All right, so we keep going. We get to 6, it adds 7, and so forth. That's the whole thing. And so I encourage you to play around with this later. Now, one thing I want to point out is that unlike depth first search, where we usually are just hopping one over and then occasionally backtracking, with breadth first search, watch where V goes. So V is there, then there, then there, then, oh, hopped over to 4, then to 5, then over to 3, then over to 6, then 8, and then 7. So it hops all over the place. Watch the V. Okay. So it's a more hoppy feeling, and that's fine. It's got this sort of non-local travel feel. Okay, so that's breadth first search. This is a super important algorithm, and I think you've got hopefully the primary texture of it, and you will also get to play around with this more later. Go ahead. Mm-hmm. Right. Right. So the question was, suppose we wanted to find shortest paths if the edges cost different amounts. Yes, this would not be a +1. It'd be a plus the weight of the edge. And then you would need to do something else with the fringe. You're right. So that you tend to go to closer places first. And that'll actually be the next lecture. And actually, what's interesting is that algorithm you just talked about is the most basic AI algorithm that you'll learn in 188 called A-star, for reasons that we'll get to at the end of that lecture. Anyway. So it's like, what does this have to do with AI and decision making? No, that's the end of the next lecture. All right. Okay, so why is this useful? What is breadth first search all about? Well, one example is this Kevin Bacon game you might have heard of. He's an actor. And so the idea is from Kevin Bacon, this started on the internet in the 1980s. The idea was how far away, if you pick a random person, like let's say Patrick Allen or Nicole Kidman or whoever, how many movies and people do you need to go between to get to Kevin Bacon? So between Nicole Kidman, you could maybe go to Cold Mountain, Donald Sutherland, Animal House, Kevin Bacon. And so breadth first search is a way one can do this. Okay. And you can even Google this. There's the Oracle of Bacon online that will allow you to find the distance to this guy from anywhere, though I will not demo it today. But breadth first search is how you would implement this algorithm, and happens to be useful for all kinds of purposes. Now, to your question, let's imagine we tried to use this for Google Maps, okay? Something like that, Apple Maps, whatever map you like. And let's say we build a graph where the vertices are intersections. So for example, one vertex would be Bancroft and Telegraph. Another one would be Oxford and Hurst and whatever else. And then the edges would just be the roads connecting the intersections. So breadth first search, as described on this slide here, would it be a good way to implement Google Maps or not? What do you think? I mean, it would work, it would tell you something. Would it give you the shortest path? Are there situations where it wouldn't give you the shortest path? Yeah. Okay, traffic. It doesn't take into account traffic. That's the one. But there's actually a more fundamental issue that's related to that. Yeah. Right. So not all roads are the same length. So it could be that if I want to minimize my number of turns, maybe I get on I-80 and I drive to Reno and then, take a left turn, then take another left turn, and then end up where I want to go, but I drove 400 extra miles. Yeah. Weighted each edge by how long it would take to get from one intersection to the next. Right. So what you could do is just weight the roads by the time it will take to traverse them. And that's basically what Google does with traffic. And in that case, you have to tweak your algorithm a little so that it's not just +1, and that'll be next lecture. So just a note, though, that this is close, but not quite what you need to do driving directions. Okay? Some roads are longer than others. Sometimes there's traffic. Maybe more fundamentally, roads take different amounts of time to traverse. Okay. So before we get to that, I'm actually going to take a break from our lofty world of ideas, and I'm going to return to the base world of box and pointers and implementations. So far, graphs we've treated as just magic, right? We don't have any specific way to write code to interact with them, which will be a problem because in project 2B, you're going to have to build your own graph class and traverse a graph. So we need some way to interact with them in code, not just as an idea. So in order to implement breadth first paths or depth first paths, those demos I've done where you get the edge to and the distance to array, we need first some kind of API for graphs. An API stands for this set of words, but it basically just is the set of methods and how they're supposed to behave. Okay. And so this is going to define how you as a graph programmer have to think. You have to use the methods that the graph gives you. And then the other thing we need to do is after we pick the interface, we need to pick the implementation. So we have to pick data structures to actually represent the graphs. And this will be like kind of a speed run version of the things we did before, where we had the list interface with the add method and the remove method, and then we had different implementations. Same deal here. And so our choices, both of them, can have really important implications on runtime, of course. So if you have bad implementation, you're going to have bad runtime. Same thing with memory usage. And then also really, really, really importantly, as you might have seen on project 2A, if you pick the right instance variables for ngram map, hopefully you were able to write weighted weight history and some weight history methods that were like 4 or 5 lines long. But if you have the wrong instance variables, then you end up with complicated loops and all that kind of thing. So having the right instance variables, or more generally, the right interface, makes it much, much easier to actually implement things. So let me give you decision number 1 for our API, which I'm borrowing from the Princeton textbook. You do not have to follow this decision when you do project 2B, but I'm going to say that all vertices have integer labels. Okay, they're just vertex 0, 1, 2, 3, 4. And in particular, they're going to start at 0 and go to some other vertex number. Okay. And so throughout this implementation, instead of saying Austin, Dallas, and Houston, this is the graph, I'm actually going to have a graph where I have vertex 0, vertex 1, and vertex 2. And if I want to remember which vertex goes with what, I'll also have a second data structure, a map, that goes from string to integer. And maybe I'll need an actual third map if I want to go, or sorry, a third data structure from integer to string if I want to go back the other way. Okay, so just be aware that we are not going to, in our lecture, allow you to build vertices that contain words. They only have integers. And you need supplementary data structures to go between them if you want. Okay. So then what that ends up with, this is the way that the optional textbook for our class from my former colleagues at Princeton put together, which is the graph class. It has a constructor where you must say the number of vertices in advance. You can't add new vertices in their API. You, in project 2B, you can add new vertices, but if you want to use this API, you can't. You can add edges, though, where I can say I want to add an edge between V and W, and it has no properties, no hair, if you're a physicist who studies black holes. It's just, there's nothing to it. It's just an edge. We also have the ability to get back the vertices that are adjacent by saying, hey, vertex 6, who are your adjacents? And rather than giving a list of integers, they decided to do an iterable. I'm not quite sure. I find this API a little awkward, but I guess they're trying to emphasize that we don't really know it's a list, but I don't know. You can put in your mind list here if you want. Behaves basically the same. And they're going to ask for the number of vertices and edges, and that's basically it. There's a little bit more stuff, but not that we care about today. Okay. So again, we have to say how many vertices there are in advance. They're only integers. They have no weights on the labels. Sorry, there's no weights on the edges or nodes. And there's no way to get back even the number of edges for a vertex. So for example, if I get back this adjacency list or this adjacency thing, it's an iterable. I can't say dot size. Okay. That, by the way, is also known as the degree of a vertex. So if I, Josh Hugg, have been in 5 movies, then I'm going to have 5 edges, and my degree will therefore be 5. I've not been in 5 movies, as far as I know. All right. I was in a snowman movie once. That's the only one really of note. All right. So an example client that would use this graph, there's no degree method. So imagine I wanted to write degree. What would it look like? Okay, give me a graph, give me a vertex. And then what I'll do is say the degree is initially 0. And then for every neighbor of vertex V, I'm going to add 1 to the degree, and then I'm going to return it. That's the whole method. And degree, again, as I said out loud, was the number of edges. So this would be an example that if the API is strictly limited to these methods and you want to know how many edges a vertex have, that's what you're forced to do. All right, any questions about this so far? So I'm hoping you're getting more comfortable with this notion that like someone just gives you a set of moves and then you have to learn how to use those moves to solve problems. It's going to happen over and over. Okay. Goal for you, try to write a client, that means a program, that will print out a graph. How would it look? Now you can't write code, I mean, you can try it on paper if you want, but just mentally try and feel out what would the code roughly look like to get this right here. Okay, so I'll reveal it to you. So first we're going to iterate from I to what? Yeah. Yeah, g dot v. So we're going to do this function here. And then for every one of those i's, we're going to iterate over the adj. Okay, so actually I used, instead of I used v and w. So v will go between 0 and g dot v. Those are the vertex numbers. Here's 0, 1, 2, and 3. And then for every neighbor of v, I'm going to print out v plus a line plus w. Though I will note that my code does not actually do the same thing here because I have extra spaces here. It's a fiction between these two. Close though. Any questions about this? This is what the code would look like to print out the graph. Here's a sort of trivial question. How could I modify this API so that printing the graph is easier for a client? This question's so dumb, I don't even know if I should have asked it. Yeah. Yeah, have a print function or a toString function. Yeah. Right. So it's kind of interesting that you have these duplicates, that we have both an edge from 0 to 1 and 1 to 0. And so this code, if this was my goal, this code will generate that. If you didn't want that, then you have to write your code slightly differently. You could, for example, say, oops, if v less than w would print, otherwise don't. Or less, yeah, less than w. Okay, so going back to my favorite picture, our choice of graph API has really important implications on the on how someone would implement something like depth first paths, breadth first paths, print, or other graph clients, programs that use graphs. So the basic moves that I, the monk, provide, these are the fictions that I'm going to provide, affects how someone else is going to use my code. And we'll come back to that in a little while. But first, I want to talk about how we actually implement graphs themselves. Okay. Now, this is a painful video, This is a painful segment, I'm going to say. I find the runtimes for this part of the lecture somewhat vexing, and you will too. So it goes. Okay. So to implement graph algorithms, we need two things, an API and a data structure to actually implement that interface. And so what I'm going to focus on is how our decision about the instance variables to represent the graph itself will affect our runtime and our memory usage. Okay. So with trees, we saw we had implementation 1A, 1B, 1C, implementation 2, 3A, and 3B. I think were the different. Maybe, I think that was the right number. Maybe I'm not quite right, but that's what I seem to remember we did in the tree lecture. Okay, so here's the 1A approach where I have a tree, and this is how we implement it behind the scenes. I have a tree. This is how we implement it behind the scenes. There's different approaches, right? And this is the one for heaps that only works for complete trees. Okay? And so our choices constrain what's possible, and they also affect how much memory we use and how much time our methods will take. So this approach is going to be very low memory and very fast. This approach is a little more complicated. There's more layers of indirection. If I want to get down in the tree, I have to traverse log number of links. This one, well, can be fast. So the first representation I'm going to get for graphs is an adjacency matrix. So in this approach, a graph is represented by a V by V matrix, where an entry is 0 if there's no edge between them, and it is 1 if there is an edge between them. Okay. Now, this will also allow us to easily differentiate a directed graph from an undirected graph. So in a directed graph, I'll have an edge from 0 to 1, but not from 1 to 0. In an undirected graph, this matrix will be symmetric. That is, for everything over here, we have an edge from V to W. We'll have the same edge from W to V. Okay. Now, this is, I would say, a little, you could argue, if it's a symmetric matrix, why do you bother storing both halves? And the reason is it's simplicity and slight runtime advantage at the expense of space. But if it really bothers you, you could just store everything above the diagonal. And since we don't allow self edges, the diagonal will always be all zeros, but it's fine. It's just twice as much memory. That's approach 1. So in this case, if I do g.adjacency of 2, so what are 2's neighbors, then it returns an iterator, or rather an iterable, I should say. So g.adj returns an iterable, and that iterable gives us an iterator, and that allows us to call next up to 2 times. And the first time we call next, we get 1. Sorry, this one right here. So 2, yeah, first time we call it, we get 1. And the next time we call it, we get 3. Okay. Now, what that means is when that method is running, the total runtime to iterate over all the neighbors of V is going to be theta V. Because if I want to know who are the neighbors of 2, I have to actually look at every entry of these. So you might imagine that it's got, remember WizPause? I know, by the way, in project 1, it was funny how many different people use WizPause literally as their instance variable from lecture. I appreciate it. That's an homage to lecture. But if we imagine that WizPause variable, the first time the wizard's going to go, nope, not there. Ah, yes. Okay. And then when you call next, it's going to hop its way over until it gets to 1. But all those wizard hops take some time. And so the overall runtime to finish iterating over the entire set of neighbors is V. And so that means if we had, say, 1,000 vertices, but each vertex has only 1 or 2 edges, then we're spending a lot of time iterating over a whole lot of zeros. But it will work. This is a very simple approach. Any questions about that? Maybe that makes intuitive sense. So here's a question you won't like. So let's suppose we have this code right here, which, as you recall, prints out our graph. So what's going to be the runtime to print out the graph if we use an adjacency matrix? And here are 4 different choices. And one way you can think about it is you can think, what's the runtime to iterate over V's neighbors? And how many different vertices do we need to actually consider? And V is just any particular vertex that's active at the moment. So I'll give you guys 1 minute to think about this problem. It's 2.5 questions today. Okay, so the runtime in this case is going to be V squared. Why? Because the time it takes to iterate over all of zero's neighbors is V. Time to iterate over all of 1's neighbors is V, 2, V, 3, V, and so forth. And so this total of V vertices that take V time, so it's V squared. Not so bad. Okay. All right. Let's see another example. Representation 2, kind of a red herring. Kind of feel like I should delete this out of the lecture. So it's so weird. I'll never see anybody actually do this in any circumstance. But you could do this if you wanted. You could create a set of edges. Okay, so we'll do a hash set of edges. And what's an edge? It's a pair of integers. Okay. So in that case, this graph would be represented by these tuples: 0, 1, 0, 2, 1, 2. So it's kind of clean. So instead of representing this as a 3 by 3 matrix with a bunch of zeros, now we represent it as 3 pairs of integers. Okay. Nobody really does this. Don't really want to talk about that much. So instead, I want to talk about the way that graphs are often done and the way that I encourage you to use for project 2B. You don't have to do this for project 2B, but I think it's the most natural. So in this approach, what you'll do is you'll maintain an array of lists that's indexed by the vertex number. In other words, it's kind of like a hash table, where if I want to know zeros edges, then we have an array where we have an entry for every single vertex, and in 0, we say, oh, okay, well, zeros edges are outgoing edges are 1 and 2. And if you wanted to do an undirected graph, then you would just see the corresponding edges the other way. So we'd have like 2 points at 0 and 2 points at 1 and so forth. Okay. And so this is the most popular approach for representing graphs. And that's because graphs that people build in the real world are often sparse. What I mean by that is that just pick a graph of anything, like a graph of the relationships between people in this class. You only know a small subset of them. So if I build that 1010 by 1010 size matrix, it's just mostly zeros. So a way to capture those relationships in a more concise way would be these so-called adjacency lists. Yes?
If our graph is sparse, we maybe consider using some kind of set so that if we want to check it.
Right. So suppose you wanted to actually deal with a less sparse graph, then yes, you might pick something else to go in the buckets, or maybe just go to an adjacency matrix if it's so dense that most of the time it's there. I don't know. It's an interesting question. And I'll say that in specialized applications, these things come up a lot. Dealing with sparsity or the lack thereof is in real world industrial strength programming is a big deal. Okay, here's the runtime that I think you'll especially not like, which is what is the runtime of print if we use an adjacency list? Okay. Now, I want to point out one thing real quick, which is that E is the total number of edges in the entire graph. It is not the average number of edges per vertex. So here E is 3 because there's three edges. Okay, good luck. Try this question. We'll see how it goes. Okay, even if you don't have it, you're going to get a chance to do the same problem again in a moment. So if you try to do it the way we did before, where it's like, well, each one takes v time and there's v of them, therefore it's v squared, you run into this interesting situation, which is, well, the runtime to iterate over v's neighbors is variable. There isn't really a big theta that's either 1 or v or something. So I could say that in the best case, there are no edges. So it's just constant time. That means as the graph becomes bigger and bigger, it could be that there's some vertices that have no edges at all. So my graph is 1,000, 10,000, 100,000, a million. I'm getting more and more users on my platform, but nobody actually makes any friends. Well, in that case, even though the graph is getting bigger, I'm not actually having an increase in the runtime to iterate. By contrast, maybe we have a group of a social network where everybody is really connected for some reason in some application. In that case, as the graph gets bigger, the actual number of neighbors gets bigger. So it could be anywhere between 1 and v. How many vertices do we consider? V. And so the runtime could be anywhere between v and v squared. So the best case is theta v, and the worst case is theta v squared. Yeah.
The outer
The average case is, well, this is in general. We don't know anything about the nature of the graph. So if we wanted to know the average case, we'd have to have some model for how the graph was generated. Okay, try again. I didn't give you that choice. I didn't say you could say best case theta v, worst case theta v squared. So if the best case is theta v and the worst case is theta v squared, which of these four should you pick to capture that? This is the most annoying question I may ever ask in lectures. Okay, this is a hyper subtle one. Okay, like I probably taught this class several times before I felt really good about this. And I still feel slightly uncomfortable because the definition of multivariable asymptotics is a little messy and I've never presented it. And there's a whole paper describing how it's a little self-inconsistent. If you're curious, ask me later. But the traditional approach here is to say that the runtime is theta v plus e. Why? Well, the best case is theta v and the worst case is theta v squared. But in all cases, I can tell you the following. The runtime is going to grow with v plus e. Okay. Why can't I just say, sorry, you might be saying, what's with e? Like, why are we summing these? Remember, e is the total number of edges in the entire graph. That's everything, all edges added together. And so I think about it this way. The work you have to do is you have to create v iterators. No matter what, you're going to have to make this function call v times. So you have to spend at least v time, even if you have a graph with no edges. So you have a graph that's getting bigger and bigger and bigger, but there's basically no edges, or maybe no edges at all, right? It's just getting bigger and bigger. For such a graph, you're still having to do that v work to make the iterators. And the other thing we need to do is we need to print e times. So for every edge, there's going to be one print statement. Okay. Now say e is very small. You have a family of graphs that you're simulating a graph that's growing, and the e grows really slow, like at log v speed. Like there's like a very small chance that any edge exists. Then as that graph gets bigger and bigger and bigger, really not going to be printing much out. And the runtime will be dominated by the creation of iterators. In the other extreme scenario, the graph's getting bigger and bigger, and there's tons of edges. Maybe even the graph is fully connected. Then the edges will dominate, and it will be v plus. Yes. Yes, we basically, the cost model was the sum of the number of iterators calls plus the number of prints. Yeah. Yeah. It's a little smelly though. So we have not been super cautious about even defining multivariable asymptotic notation. Okay. So the way I interpret this is just the slide version of the same. So remember asymptotics is about as our input get bigger, but there's many different ways they can get bigger. So one example, again, is that we have a very sparse graph where e is growing slowly, but v is growing rapidly. Okay? But they're both growing without bound. Or we have another example where e is dense, or the graph is dense. So e grows quickly, every vertex is roughly connected to every other. Okay, so you can reread this, same stuff I said out loud. Probably should have had this on the screen when I said all that. Okay. You could do this exercise for many other operations for all three of the different implementations, and you will arrive at this table that will be potentially somewhat challenging to come up with. Okay, but what I really drive home, the actual really important point here, the thing that isn't just like maybe a small number of points on an exam, is that the choice of implementation matters. It changes the runtime, sometimes somewhat dramatically. And a lot of graph algorithms, I want to note also, often rely on this adjacency method. Even if you don't have a method that looks like this, something like it. Okay. All right. So if you wanted to look at how graphs are undirected graphs are implemented in the Princeton library, it looks something like this. You're welcome to use something very similar for project 2B or not, whatever feels right. Okay. Okay. So let's talk a little now about our graph traversal implementation. So we have these breadth first paths and depth first paths algorithms. And so I want to know, how do those behave? Okay. And how are they implemented? So the Princeton approach, which I think is nice, but you don't have to do this on 2B, is to decouple the type from the algorithm. What I mean by that is they have a graph class that doesn't do any kind of searches. And then they have classes like paths that take a graph and a starting vertex and then like think about the graph. Here's paths.java. Okay, you pass this graph to this Bodhisattva here. She reflects on the graph, learns all of its truths. And then you can ask her questions. Is there a path to V? What is the path to V? And so forth. Okay, I think this is a really neat, clean idea that I encourage you to try on 2V. That's how I did it. But I bet if I asked my TAs, I bet a lot of them didn't do this. And I bet they just had a graph class that had some methods. So either way you want to do it, you can. But I think this is an interesting case study in library design. Okay. So you create a graph object that represents the graph. You pass it to some object that thinks about graphs. And then you ask that object about the graph. So for example, paths. Tell me, I want you to think about all the paths from 0. Right? And then I can ask and then quickly get an answer. After this processing step, we say, is there a path to 3? Or what is the path to 3? And this is reflective of what you did, hopefully, on 2A, where the constructor for Ngram map, it did the work. It thought about what's in the data file, and then you can ask it questions really quickly. This is the same notion. Yeah. Oh, sorry. That's all. And I didn't. So let's run depth first paths one more time so that we remember what this demo looked like. Come on, Google, I believe in you. Oh, we got to start though. That's pretty important. So this was depth first paths, which remember the goal here was I want to start from some source and collect information about every reachable vertex, how to get there, and some path there. So we start by going to 0, then we go to 1, and then we go to 2, then we go to 5, and so forth. So we're just depth first traversing this thing. And here's all the little details about marked edges and so forth. We did all that before. Okay, the next call we make is going to be 4, then 3, and then where do we go to next? We're going to return. Where do we go next? 6, 7, back to 6, 5, 8, 5, 2, 1, 0. Okay, that's depth first paths. And if this isn't totally familiar to you yet, after Wednesday, I would have encouraged doing this, but today, definitely do it. Make sure this all is like rolls off the tip of your brain. Does your brain have a tip? I don't know. Could be a problem if it does. You know, when babies are born, they often have weird shaped heads. If you should look for a picture of a baby that was born less than like 5 minutes ago. Like they have a cone-shaped head often. Depends on how big the baby is. So you do have the tip of your brain when you're first born, maybe, depending on how big you were. Anyway, back to life and not childbirth. Okay, so depth first paths. The approach is, this is the implementation that will be done with the graphs API that Princeton provides, is like this. So we have a marked array and an edge 2 array. This is the crystallized knowledge of the Bodhisattva, right? After she's considered this graph, this is everything that she's learned. What I'm not showing here is the initialization of marked and edge 2 because it's not interesting. It doesn't fit on the slide. And then the first step after setting up the empty place for the knowledge to go is to call DFS on G of S, on S vertex of G. How does that work? We set the marked array to true. Then we iterate all of these vertexes or as neighbors, all of these neighbors in the graph. And then if that vertex is not marked, the neighbor we're thinking about, we set the edge to and call DFS. That's the whole thing. Okay. So all that recursion that you painfully learned throughout 61A, 88, maybe E7, it all actually, maybe CS10, this is why it's useful. It's useful because real data structures are often recursive, and this is a much more natural implementation that you'd get elsewhere. Okay. So how would we write path 2 and has path 2? It's a question you might ponder. It's not a thinking question during lecture, but you, video viewers, you can try if you want. So what it might look like is something like this. So has path 2 is very easy. You just ask, is it marked? And then path 2 is a little more complicated. So if there is no path, we return null. Otherwise, I'm going to create an empty list. And then I'm going to walk down the path. So the Bodhisattva, although she knows a lot about the graph, she still has to walk through that array because she doesn't have all the paths pre-computed, but she does have all the knowledge she needs to recreate them quite quickly. Okay. So what do you think will be the runtime for the depth first paths constructor right here? How long does it take to actually do the process? Give me a big O bound. And I'm going to assume the graph uses an adjacency list. This is a pretty challenging problem. So I'm going to give you guys 90 seconds or so to think about it. Not enough time to actually solve it, but to start sniffing out the feeling of the answer. The S is the start vertex. So if you start at 0, S is 0. Okay, so I'm going to spoil this. This is a pretty challenging one. I'd say somewhat more challenging than our print example, but not by much, but it's a very similar pattern. So it turns out that, and actually, if you look at the video from 2 years ago, I had a slight error here. So it's very subtle, even I'm going to mess it up. So big O of V plus E is the answer. And the reason is the following. So each vertex is visited at most once, which is big O of V. And then each edge is considered at most twice, because as you're working through this graph, when you get to a vertex, you're going to consider the edge once on the, like this side of the edge, and once on the other side of the edge. Or if you want to do it sort of in terms of cost models, and this is the part that I was slightly sloppy about in the 3-year ago video, think about it this way. The number of DFS calls is going to be no more than V, and the number of marked calls will be no more than 2E. And so again, as before, the cost model is the sum of two things, sum of DFS calls and the sum of marked checks. Okay. Challenging for sure. Very ample ground for office hours and exam prep questions. Hard question. Could we say the runtime is big O of E? The argument here is we could only visit a vertex if there's an edge to it. So could we just say it's big O of E? This is kind of a stupid question, but I wanted to raise it because it comes up. Or like a pedantic question, I should say, not stupid. Yeah.
I just have a question. Does the previous slide have anything to do with the handshake theorem?
Good question. I'll think about it. Okay, so it turns out you can't say it. It might be tempting to say if you have a graph with no edges, why would DFS take any time? Well, the silly answer in Java is that creating the all marked false array up here, it actually takes V time. So even if there's no edges at all, you have to spend that time for the constructor. So on a technicality, you can't say E because of that. Okay. All right. Yeah.
We say DFS takes OV.
Say DFS takes O of E. Ooh, that's an interesting question. Sure, I think so. Because if you make your first DFS call, you get to the root. All you do is set V to true, and then you iterate over nothing. So yeah, be quite quick. And constant time would be big O of E for sure. Cool. Okay, so the runtime of this ST paths problem solution, depth first paths, it's V plus E time. And I didn't say it out loud, but it's V space, which is the amount of space you need to store. Okay. So that's based on the cost model of adding the DFS calls and the marked checks. And we can't say big O of E because we're creating this marked array. We also can't say it's theta of V plus E in this case. And I didn't say anything about that in lecture, but if you want, think about the example of a graph that has no edges touching the source. In that case, this runtime, it wouldn't grow exactly as V plus E. So we upper bound it to avoid having to talk about silly cases like that. Okay. All right. Breadth first paths, if you're curious what that would look like, it's something like this. We create a fringe, which is a queue. We enqueue the S vertex to the fringe. As long as the fringe is not empty, we dequeue and do something very similar. Okay. Now, again, this is too much code to digest in 1 minute, let alone, or in 3 minutes, let alone 30 seconds. But it's a classic algorithm that you'll have a chance to play around with in the future in our class. Okay. And so if you do the same analysis, and again, here, rather than putting you through yet more analysis exercises, you can show that it's V plus E time. It's the same exact cost model as before. There's V calls to dot next. And then there's big E checks to each edge. So it's almost the exact same algorithm. It's just you're doing things in a slightly different order. If you had a queue that was slow, that getting the next item off the queue was slow, then this doesn't work anymore. But I'm assuming the queue is constant time. All right. So the last thing I want to talk about today is layers of abstraction. So I said earlier that our choice of graph API has really big implications on how someone implements depth first pass, breadth first paths, right? So if the vertices are labeled from 0 to n-1 versus being labeled Jeff, Tom, and Frank or whatever, in that case, you're just gonna have a different kind of code, okay? And we also saw that our choice of how to actually implement the graph API has really profound implications on the runtime. So depth first paths on adjacency list based graphs was big O of V plus E. But what happens if we were to swap that out and we say, okay, sorry, the layers, by the way, I guess I should have a picture of these layers. So here, these monks, they create a reality, which is graphs for somebody else who's using the graph class. But in turn, this graph class, it is created by monks who actually think about it as an adjacency list. That's the layers. So maybe we need like more monks over here who are doing the world for these monks. But that's how things work. Now, what happens if these monks decide, actually, we want to use an adjacency list? Or sorry, adjacency matrix. What happens to the runtime? Well, I don't have any time to have you actually think about this. But it turns out that you can show that it's B squared. In the worst case, we're going to be iterating over the neighbors of every single vertex. Because in a graph where things are connected enough, it's going to take us B squared time. Okay. So if you use an adjacency matrix, if that's the underlying secret sauce of your graph, then instead of being V plus E time, it's going to be V squared. And so that means on sparse graphs, your code will be unnecessarily slow. So we're always going to use adjacency lists unless we say otherwise. And you should use adjacency lists on project 2B. Yeah. It takes V squared space for the matrix itself, but only V for the problem solving process. Yeah. Okay, wrapping up. So we saw today a few things. One, we saw breadth first search, which is using a queue instead of recursion. And then we saw the graph API, which is out of the Princeton's algorithms book. It's a clean API, but very minimal. You're welcome to replicate it in project 2B if you'd like. Now, the choice of API that you pick will affect the way the rest of your code works. And so at this point, you know everything you need to work on 2B, which we'll get out as soon as possible. The QA is done today, so we'll get that out there. And 2B is going to be an interesting project. I'll make a video about it where you're going to be free to make all the choices you want, top to bottom. The spec's pretty short. You pick the data structures. You convince yourself it works. It's still an auto grader, but yeah, it's a much longer path from spec to answer. Okay, see ya. All right. Yeah, see you on a double see ya.